Peter Bosa. He's going to be presenting on Metro's macro level DTA. And Peter Bosa is a principal researcher and modeler for Portland Metro, where he oversees the transportation model development and application. Peter has over 15 years of experience in transportation research and modeling application. Recent work includes several DTA deployments in the Portland Metro region, including the I-205 tolling study, interstate bridge replacement, and the upcoming West Side Corridor multimodal study. So Peter, I'll go ahead and kick it off to you for the presentation. You're on mute, Peter.
I know, so I got muted. Am I still muted? Okay, looks like I'm unmuted. And you can see my presentation, Randy?
Yes, you're good to go.
Okay. All right, excellent. Well, thank you. Thank you for having me, everyone. I'm gonna just spend a little bit of time today talking about our dynamic traffic assignment tools and application in the Portland Metro region. I know that the description said our macro scale DTA. I think that macro scale was meant more in terms of geographic spread. So the entire Portland region or large portions of the region, it's not necessarily a macroscopic DTA. But we'll get into that here in a bit. So, okay, so this is kind of where we'll be going. A little refresher on what is DTA, some of the history behind the development for Metro, and then we'll get into how we've been applying it, mainly what we do in terms of calibration, and finally, you know, some of the applications we've had here at Metro, and some Q&A if we have time at the end. Okay, so just a quick refresher. This is what I was referring to when I said macro scale. So we have a continuum of resolutions of modeling tools, right? When it comes to assignments, at one end, you have your macro simulations. These are often referred to as static assignments. They're tried and true tested assignment tools. They've been around for decades. They're usually integrated with your trip-based models. They do great for evaluating route choice capability. They run very fast on our computers, and they're kind of the workhorse of our long-range planning here at Metro. Some of the cons is that these tools will they'll assign all demand regardless of network capacity. So when you move into future years or even today in heavily congested time periods, these tools will assign the demand to the facilities regardless of the available capacity, and you can often end up with volume to capacity ratios that exceed 1, which an engineer would cringe at. They also, while they'll do a pretty good job of pinpointing where bottleneck locations might occur, they do not do well with simulating the queuing that occurs because of the bottlenecks. And so because of that, they do a poor job of capturing congestion impacts upstream from your bottleneck locations. And so they probably they definitely underestimate travel speeds. They overestimate speeds and underestimate travel times for very congested corridors. And then I have kind of a list of some of the common tools that are static assignments. At the other end of the spectrum, you have your micro simulations. These are very precise, highly detailed computer simulations. Often the vehicles are almost like agents. They're being modeled one individually. They can be assigned specific driver behavior, and they're being simulated in almost real time. So very small fractions of sometimes even sub-second. They're very time consuming to develop and calibrate. They take a lot of time in order to make sure they're functioning properly. They're computationally very intensive because you're modeling many more single individual objects. The vehicle paths are often fixed, not always, but the traditional application is you get a set of vehicle paths from something like a macro assignment, and then those paths are fed into the micro simulation, turned into individual vehicles, and then it's left up to the operator to determine how to deal with situations in which the demand coming out of your micro assignment might be too far exceed the capacity capabilities of your facility. And so they can sometimes overestimate the amount of congestion on a facility because there's not really that release valve of alternative routes to look at. I'm speaking in generalities here. I know that Chayton would probably, raise his hand and say, oh, wait, our tool has ways around that. But this is just, just kind of in general. Then you have this sweet spot, the Goldilocks spot, the meso simulations, dynamic traffic assignment. Occurs. There are macro level, macro scale traffic assignments, DTAs. There's some that act more like a micro simulation. But we kind of just group DTA in with this meso simulation description where you're modeling large areas similar to the macro assignments. You're simulating individual vehicles. There's even some generic behavior associated with some of those vehicles. They're capacity constrained, so you're never going to get a VC over 1. They do a great job of identifying bottleneck locations and the queues associated with those bottlenecks. In general, they give us the opportunity to evaluate operational characteristics at a much larger scale than we're used to. Operational characteristics of your highway system. And so below is just kind of a list of some of the products that are out there. We've been using Dynamec quite extensively in our region. But I've used all of these other tools that have listed below, and they all have their advantages. So this isn't by any means a judgment call. It's just we use Dynamec in our region. So we've been actively engaged in DTA development here at Metro since basically for over a decade, since 2010 is when we really got going. We spent a lot of time and resources developing networks, actually all the way down to the lane and intersection level. So when we developed our first networks, we were adamant about getting turn pockets correct, turning movements for lane-to-lane turning movements in intersections, the length of turn bays, as much detail as we could possibly get into our large regional networks. And part of this was because there had been this promise for DTA out there for a long time. It's a tool we've wanted to use. Unfortunately, until the last maybe 4 or 5 years, I would say that the promise of DTA exceeded kind of the ability of the tools to function in a manner that was conducive to our planning. So basically what I'm trying to say is that the computational runtimes of these DTAs was significant. It didn't make them practical to run at a very large scale. And there were also some issues behind convergence and all of that aside, we still found a couple of test cases where we could deploy these tools. The image here shows some of those deployments. There was as part of the Barber study, we actually did a SHARP grant where we looked up. Somebody's unmuted real quick. Okay. And then we did one for, it looks like a rather large area. This was actually, sorry, the yellow one was produced as part of the division Foster study. And we actually PAL study, and you see this little red area here. This was actually the little DTA section that we ended up using, and it was integrated with a micro simulation. Okay, so after over the last couple of years, our developers have been hard at work. They've improved the assignment capability of their tools. There's multi-threaded assignments now. They took some of the more complicated calibration features like signal optimization and automated those. There's methods now for dealing with supersaturated conditions. So even if your demand exceeds capacities, the tools are able to kind of massage it in such a way that they can still reach convergence in a relatively reasonable amount of time. And they have the capability now to scale to much larger areas than before. So we started a project a few years ago trying to figure out what's the quickest way that we could deploy a DTA at a large scale. What are the features that are most important for a DTA? And we basically came up with this quick launch DTA idea with our friends at Inro, the developers of Dynamec. And the whole idea was we wanted to simplify, standardize, and economize, basically take advantage of repeated applications of our DTA tools. And during this project, what we learned was that a couple key takeaways. One, it should be at the top. Ramp meters are really important across all the tools that we've ever tested for DTA. If you can get if you want to get your freeways validated well to observable data, you really need your ramp meters in there. They're critical for controlling the flow of traffic onto and off of your freeways. The presence of signals matters, not a surprise, but the actual timing plans are less important when you're looking at a larger scale. So generic timing plans seem to work fairly well. And so you don't have to worry about necessarily getting every signal timing plan correct in your model, which is great. And then we also found that turn-based didn't really improve our model validation, at least at a higher level. We do have lane-to-lane movements in our model. We do have turn-based lengths, but we found that if needed, if we had to, we could use a tool that basically creates generic turn-based, standardized like 100 feet, determine the locations where they should go, put them in, and that seems to work just as well as having actual representative network, a real life representative network. We also did some work around how do we move from our trip-based model, which it produces the trip tables that feed the DTA. How do we move from that into the DTA? Our trip-based model is run at the regional level. We knew that the DTA, the final applications would tend to be at a sub-regional level. Does it make sense to go from a regional trip-based model to a sub-regional, to take a sub-area cut of those networks and then move those into DTA? Or does it make sense to take your regional trip tables, move those to a regional DTA, and then use that to take our sub-area cut? And we basically landed on the latter. Go from the regional DTA to a sub-area DTA, and I'll talk about that here in a second. So this is an example of an application for the I-205 project. In this project, we start with a regional DTA. We haven't optimized all the signals or anything. We're not too concerned about even validating well at the regional level. Instead, what we're doing is we're loading all of our static assignment trip tables onto the regional network, and we're just running it just to kind of get a capacity constraint on the demand in the network. So this way, when we do our sub-area cut, we know that the demand feeding into the sub-area won't exceed the carrying capacity of the network, and it helps improve our validation of the sub-area later on. There's an efficiency with reducing the demand to the carrying capacity of your network before you start doing your hardcore calibration and validation. This is just kind of an idea of some of the attributes involved with the Dynamec product. It is lane-based. So you can see here, every facility, it is lane to lane. You can actually see the turning movements at intersections. And you can also see here, this is the phasing for the signal at the intersection. So there's a lot of detail in these networks, far more than in our static assignment networks. And this is what I was talking about, all the time that we spent coding those networks at the beginning. Okay, so this is just, these next two plots are basically just showing, they're from portal data on I-205, and it shows the relationship between speed and density on your freeway, and I think volume and speed and flow rate. And so I put these in here because they show what's happening in real life, and they also show what the DTA is doing. So in real life, this is a facility on I-205. As it fills up with traffic, it can maintain a pretty steady speed up into a certain point. You'll notice here, and our flow rate keeps increasing almost up to 2,000 vehicles per hour per lane, but not quite. I'd say maybe it maxes out at around 1,750, 1,800. But then we see a huge drop off in speed and the flow rate starts to decrease. So what's happening here is you're filling up the facility with traffic. Because of that, the congestion is causing friction, slowing vehicles. And as a result, you get less and less vehicles through the corridor. So that's a primary difference between a DTA or micro simulation and your static assignment. The static assignment would show slowing speeds, but your flow would still increase. It doesn't have this ability to decrease flow as your congestion builds. So the DTA is basically capturing this as you reach a critical mass, your flow rate decreases, your speeds decrease, and that gets represented in the we'll see that in a little bit. So here's just some of the characteristics that we tried to validate against. We lifted many of these from the VISM protocol that was developed for ODOT, microsimulation protocol. Because this is a different tool than microsimulation, we're a bit more relaxed, especially when it comes to some of our GEH and other goodness of fit statistics. But you can see here that we're still trying to go for a pretty good fit, high R squared, low GEHs where possible on counts. The same with the travel time. This is actually something where we can be a bit more in line with the VISM protocols, where we look at the travel time calibration criteria that are set out there. So we try to match the travel times within the DTA to that that we've observed with INREX or HERE data, and we try to fall within the prescribed ranges. So within a minute for travel segments that are 7 minutes or so, and within 15% if it's longer than 7 minutes. Here's an example. So when we're calibrating our DTA, we're really looking at three things. We're looking at counts, we're looking at travel times, and then we're looking at these things, our space-time plots, which show the relationship between speed and volume. On your freeway, they're really good at capturing bottleneck locations. So here, for example, this is I-205 southbound in the AM near the Abernethy Bridge in Oregon City, West Lynn. This is the INREX data. As you can see, as the colors get darker, that means it's slowing. We see a bottleneck occurring right around 7 a.m., extending back almost to 82nd Avenue, at least through the 9 a.m. for the AM peak period. We see that here in the dynamic model as well. I think this shows that we've done a pretty good job of calibrating this model so that the bottleneck location is captured, and then the actual shape of the queue spilling back, the extent of the queue, the duration looks very good. This is another example where we feel like the dynamic model is doing the right thing and is actually has there's better resolution than the INREX data. So the INREX data is much more general. The dynamic model shows the queue, I think, in higher detail. And then this is, once you've got your DTA established, you can start doing comparisons. So this is a 2015 base year. We already have congestion at the bridge spilling back in this corridor. By 2027, under a no build scenario, that congestion only gets worse. And by 2040, assuming a no build, we just have complete congestion in this entire corridor. And here's an example where we have done some analysis with a build scenario. We added capacity in the corridor. As a result, the bottlenecks have been alleviated, and you can see the queuing is gone, free flow speeds through most of the corridor. So if there's any takeaway, I'm trying to do a time check here. I probably have maybe 5 minutes, 2 minutes. If there's any takeaway, if somebody asked me, what's the biggest difference between the DTA and your static? assignment, I would say that the biggest differences occur not in your scenarios where you've added capacity and alleviated your congestion. It's in the scenarios where you have a lot of congestion. So when you have a lot of congestion, the static assignment will tend to push more vehicles through a corridor and overestimate the speed at which they're traveling. The DTA, however, is capacity constrained. And so what happens in really congested corridors is you get much less throughput. So in this example, we're getting about 25% less volume through our no build scenario. You can see that our two build scenarios are quite similar between our static assignment and our DTA. And that's because we've added enough capacity that there's no longer bottleneck issues. And both models do a fairly good job of modeling that type of a condition. But in the highly congested time period, the DTA is more responsive to the congestion. We see much more diversion in our no build at slower times or longer travel times, slower speeds. So some of our applications in the region, appropriate application, sub-area and corridor level analysis of just vehicle traffic. So the DTA, while it can have transit vehicles in it, it's not doing an actual transit assignment, meaning there's not people walking to transit stations and boarding on the vehicles and continuing on. So this is a tool right now that's just meant for vehicle traffic. It's great at studying capacity changes, maybe some operational changes related to signals or metering, and we've been using this tool extensively for looking at pricing in our region. They're great for identifying maybe intersections for mitigation analysis. They're time period specific, so that is a shortcoming. You have to develop these models for specific time periods. So like an AM peak or a PM peak, they're not all day. And moving into the west side study we have coming up, we'll be looking at potentially ways of using DTA for local air quality analysis. What we have found right now, not practical for full regional implementation. There's no feedback mechanism with the travel demand model, so we're not going to see mode shifts related to the DTA. It's not going to be feeding into that. There's no transit component to the DTA. So it's more time and resource intensive to establish than our regional travel demand model. There's much more calibration time, it's more akin to a micro simulation than a static assignment when you're talking about calibration time. You have to calibrate each application of the DTA, and you have to calibrate each time period being modeled. So this adds time. And frankly, at the end of the day, this just becomes another tool that supplements the rest of your tools. So this is a tool to supplement our regional travel demand model, not replace it. And so a couple of the projects that we're using this on, the I-205 studying project, looking at pricing, the tolling study, the interstate bridge replacement, RMPP, which is a large pricing project, and then the upcoming West Side Corridor multimodal study, which is US 26. And I'll take questions if there's time. I apologize if I went over my allotment.
No, you're good on time. We have a few minutes. So if anybody has questions, either drop them in the chat, or I think the group is reasonably sized here. Go ahead and feel free to unmute if you have a quick question. All right, not hearing or seeing anything.
Well, feel free to send me questions if you have any. Reach out to me if you have any questions about this application.
Chayton did ask, were the fundamental diagrams for AIMSON or Dynamic?
The fundamentals, you mean these? I'm not quite sure what he meant by fundamental. So the everything we've shown here was in Dynamic. If it was model related, it was Dynamic. At least on this, but we haven't done an application with AIMSON. We've done applications with Dynasty, DTA Lite, Dynamic, of course, and I know that Chayton has actually done some applications using the Zoom and some of the built-in DTA packages there. Oh, okay. the shape of the speed flow. Yeah. So this actually, I actually have a spreadsheet. So that's a Peter Bosa spreadsheet that produced this. Yeah, this is great. I love these. The spreadsheet is excellent because what it allows us to do is look at, if I go section by section, station by station, and create these models, I've found that the flow rates rarely approach 2,000 vehicles per hour per lane. And that is actually the standard flow rate that we use, or capacity that we use in our models, is 2,000 vehicles per hour per lane, like on our freeways. And after having created these plots for enough portal stations, I think it's safe to say that it's rare that you see that type of flow rate in our region. And it's led us to maybe reconsider some of the maximum flow rates that we would use, not only in a DTA, but also in like our static assignments. And I have a spreadsheet that does this stuff. That's a presentation on its own, but it's a very useful tool.
Yeah, I think that's really important, Peter, and it really goes to stress how important local calibration is for these models. Because we have data down in California that some of those freeways are pushing 2,200 plus vehicles per hour per lane. And so, yeah, we're certainly not getting that capacity here in the Portland metro region.
Randy, do you think that's like a geometry issue, a facility issue, or is that more like a driver behavior issue?
Oh, I think it's a combination of both. Having driven down there, there's definitely a little more aggression in the driving population than up here.
They're not Oregon nice like this, right? I should just label this Oregon nice.
There you go.
Lots of space between vehicles.